Hey everyone, this video is going to be a quick derivation of our three equations of motion for constant acceleration. The first equation is actually quite simple. We're just going to start with our definition for acceleration, that the acceleration was equal to the change in velocity over the time interval. And that change in velocity we can rewrite as v final minus v initial over our time interval. And then we just rearrange it to say if we're wanting to find the final velocity, Vf, that's going to equal our initial velocity plus my acceleration multiplied by my time interval. This is our first important equation of motion for constant acceleration. I'm going to refer back to this later, so I'm going to number it equation 1 right off the bat. Our next equation we actually get by considering the velocity versus time plot for constant acceleration. Forgive all of the abbreviations, but I'm just trying to be a little short. So if we were to plot the velocity versus time, so time is our parameter in the x-axis and velocity is our parameter in the y. We'd start with at some initial time ti, some initial velocity vi, that would be our point right there, and then at some final time tf, we have some final velocity vf. That would be our point. Let's see if we can line that up right there. And then in between the two, we have a perfectly drawn straight line with perfectly magnified points to make our point clear. Now, the displacement is actually defined as the displacement is the area under that curve. So, and I'm using curve in the mathematical sense. It's a straight line, but we call it, a curve in the plot. So if we sort of picture this area all the way under here, from here to here, I'm actually going to split it right off the bat into two pieces. We have this rectangle, and we have this triangle. So we find the area that's under our velocity versus time curve. That's going to be our displacement. That's true in general. Here, when we have constant acceleration, that just gives us the straight line, and it makes it easy to calculate. So our area then is going to be our displacement. So we can just start by writing our displacement, delta x. That's got to equal the area of our rectangle plus the area of that triangle. Now our rectangle is just base times height. If we look back at this plot, we see that our base is our time interval, delta t, tf minus ti, and our height is just the initial velocity vi. That's how high we are from the x-axis, where y equals 0. So our area of our rectangle is going to be vi times delta t. And the area of our triangle now, well, area of a triangle is 1/2 times the base. The base is delta t times the height. The height was vf minus vi. Again, if we look back at this, we see that our height here is vf minus vi. Now, if we also look back at our very first equation that we were using, vf minus vi, that's acceleration times time. So we'll make that substitution in this equation as well. So we get that our displacement, delta x, is vi times delta t plus 1/2 times delta t, and then vf minus vi, that was our acceleration times delta t. So those are all multiplied together. That means I have delta t squared. I'm also going to write our displacement as xf minus xi. That's just a step ahead so that it looks like the way I want it to look in just a bit. Plus 1/2 times acceleration times delta t squared. So we get finally that our final position is equal to our initial position plus vi times delta t plus 1/2 times the acceleration times delta t squared. If we just cover up that acceleration part, well, we get the final position is the initial position plus the change in position for constant speed, that's the rectangle, plus the change in position for accelerated motion, 1/2 at squared. Looking back at this plot, if we just had constant speed, we would only be calculating this rectangle's area. We're adding an additional area that we get by also going faster and faster and faster from our initial speed. This equation here is our second important equation for constant acceleration. Both of the equations we have so far include a parameter of time. There might be problems in situations where we don't want to worry about the time that it takes. So what we're going to do now is take those two equations and mash them together so that we can get rid of that time parameter. We'll start by rearranging equation 1 in order to have the following. We rearrange equation 1 to get our time interval. Well, that's just VF minus VI over A. If you need to, pause the video and go back to that, or just refer back to your notes to see how we can rearrange that to get that expression. Then we'll substitute this into equation 2. What we get when we do that is we say, okay, well, we've got XF is going to equal XI plus VI times T. Well, now T looks like this, VF minus VI over A, plus 1/2 AT squared. Again, now T is going to be VF minus VI over A, and don't forget, we've got an exponent there to square that. Now we just have a lot of algebra to do, so get ready. We're going to take this term and distribute it through. So I'm just going to move my equal sign over here just to give me a little bit more room. We still have XF equals, we've got XI plus VI VF over A minus VI squared over A. And then before I do anything, well, let's see, we're going to write 1 over 2A VF minus VI squared. So what I did was I said there's A squared on the bottom here. I'm going to pull that out. I've got A on the top. That gives me just A on the bottom. I haven't done anything else with this. Now we're going to have to FOIL that out. Make your algebra teacher from middle school proud. XI. I'm just recopying the first few terms. VI VF over A to make sure I have them nice and neat. VI squared over A. Then I have 1 over 2A. When I multiply these two terms together, I'm going to get VF squared minus 2 VI VF plus VI squared. How's that look? Make sure we can see that. Now I'm going to have to distribute this 2A into all those terms. I'm going to get to a point, I'm actually going to go landscape for this one to make sure I have enough room. We have now distributing that 1 over 2A through. We're going to say that XF is equal to XI. Again, these first few terms are just copying things down from before. Minus VI squared over A plus VF squared over 2A. Yep. Minus VF VI over A. I think I switched these from my previous, but of course it's multiplication, so it doesn't matter which order I am. That's just a little mental error on my part. Plus VI squared over 2A. This is what we get from distributing 2A through. The reason this is only A is because we had a 2 on the bottom and a 2 on the top. So, and again, I switched those, the order of those, but that doesn't matter. The nice thing that this gets us is that this term and this term are exactly the same. And I'm adding 1 and subtracting 1, so I might as well not do anything. I can cancel both of those out. I also have a minus VI squared over A and a plus 1/2 VI squared over A. So when I combine those two terms, I'm going to get minus 1/2 VI squared over A. So doing all of that simplification gives me the following. XF equals XI plus VF squared over 2A minus VF squared VI squared over 2A. Now I want to rearrange this so I get my VF squared term all by itself. So I'm going to start by saying XF minus XI equals, I'll pull out 1 over 2A. That leaves me with VF squared minus VI squared. And then after I do that, I can say that the 2A multiplied by XF minus XI, that's going to give me VF squared minus VI squared. And now my last step to rearrange that is going to be getting VF squared all by itself. VF squared equals VI squared plus 2 times the acceleration times, I'll just write delta x squared because that is XF minus XI. Not squared, excuse me, just delta x. The VI and the VF are squared. This is my third equation that is useful for constant acceleration, just to have them all on the screen at once. Our others were Vf equals Vi plus acceleration times time. That was what we called equation 1. And we had xf equals xi plus vi times time plus 1/2 acceleration times time squared. That was our second equation. So those are the three useful equations. Again, delta x has nothing. That was a mistake on my part. Three useful equations for constant acceleration.